Welcome to our lecture online. For our next example, we've changed the resistance to 4 ohms. Now that's probably going to change the kind of damping we're dealing with, and we'll find out in just a moment what type of damping we have in this circuit. The circuit is the same. The only difference is we've changed the value of this resistance. I'm not sure how many parts I'm going to need, so let's start with part 1. And we should start with finding alpha, omega sub naught, the initial current, the initial voltage, and the voltage to steady state, and of course what kind of damping we're dealing with. That's a good start. Once we've done that, we're then able to find the voltage as a function of time and the current as a function of time. Also, these equations right here could be handy. Notice that the voltage as a function of time is simply equal to the sum of the transient voltage and the steady state voltage. Same with the current. It's going to equal, and maybe in this case we don't have that going equal to 0, so we'll go ahead and put it like this. So here what we can have is we can have the initial, we can have the transient current plus the steady state current. Again, we'll find out if any of those are 0. And of course the relationship between the current and voltage through the capacitor and the voltage and the change in the current for the inductor. All right, so this is the voltage across the inductor and this is the current through the capacitor. All right, what do we do? Well, let's start with alpha. Alpha, by definition, is equal to R divided by 2L. Okay, let's see what we have here. So in this case, R is equal to 4, and 2 times the inductance, and the inductance is equal to 1, and so that's going to be equal to 2. Now we find omega sub naught, and by definition, omega sub naught is 1 over the square root of L times C, which in this case is 1 over the square root of L, which I believe is 1, and C, which is 1/4. Notice that would be 1/4, take the square root, is 1 over 2, that becomes 2 as well. And notice that these are equal to each other, so therefore alpha equals omega sub naught, which means that we're dealing with critical damping. When we have critical damping, the general equation will look as follows. It'll say that the voltage as a function of time is going to be equal to the transient part of the voltage, which is going to be A1 plus A2 times T times e to the minus alpha times T. And of course, we have the steady state voltage as well, which we need to add. And so in this case, what we need to do is find alpha, which already we did. Then we have to find A1 and A2 and the steady state voltage. So next what we should do, of course, is find the initial current, the initial voltage, and the steady state voltage. So take a look at our circuit right here. Notice when the switch is closed before we open up at t equals 0, we have a closed circuit. Current is flowing around the circuit. The inductor will not oppose the current because there's no change in the current. So initially that's like a short circuit here. And so using Ohm's law, we can then write that I is equal to V over R. So in this case, the initial current is going to be equal to the source voltage. I'll go source voltage divided by the total resistance in this case. So source voltage is 24 volts, and the total resistance will be the sum of this resistor plus this resistor, which is 4 plus 1, which is 5. Of course, that's equal to ohms. And 24 divided by 5 would be 4.8. So that's 4.8 volts, or amps for current. All right, so now we have the initial current. How about the initial voltage? Well, the initial voltage across the capacitor would be the same as the voltage across this resistor right here, because they're in parallel. And we can then say that there will be a voltage divider. So we can say that the voltage across the capacitor, which is initial voltage, is equal to the voltage of the source times the resistance of this resistor, which is 1, divided by the total resistance, which is 4 plus 1. So it's 1/5 the source voltage, which is equal to 24 volts divided by 5, which is 4.8 volts. Kind of interesting that those two numbers are the same. So now we have the initial voltage. How about the steady state voltage? All right, once the switch is open, no current will flow to this resistor. The current will not flow through this circuit, but there's a capacitor here, and it's a series circuit. So eventually the capacitor will fill up. Once the capacitor fills up with charge, the current stops flowing, so there's no voltage drop across here, no voltage drop across here, so the voltage across the capacitor must equal the voltage of the source. So therefore, the steady state voltage across capacitor will be 24 volts. So now we have all that information. We're now ready to find the constants. So now we see that we have alpha, which is equal to 2, but now we need to know the constant. So what we're going to do is we're going to say the voltage when time is equal to 0 is equal to, and we have that right here, which is 4.8, which is equal to this function right here with t equal to 0. Well, when t equals 0, this drops out. When t equals 0, this becomes 1, so we have A1 times 1 plus the steady state voltage, and the steady state voltage is 24. So that means that A1 is equal to 4.8 minus 24, which is equal to minus 19.2. So now we found A1. How do we find A2? Well, we can do that by probably finding the derivative of that voltage. So what happens when we take the derivative of that? All right, let's take a look. Is that how we do it? V, I, C, D, V. Okay, yeah. So what I'm thinking here is if we take the derivative of the voltage and we have this equation right here, we can relate dV dt to the current, and we have the initial current, so then we can find the initial condition with the derivative of the voltage. So let's do that. So dV dt is equal to the derivative of this. So in this case, that's going to be equal to, the derivative of this is of course 0. The derivative of this is going to be, well, let's see here. We have a product. We have to use the product rule here. So we take the first, A1 plus A2 times t, times the derivative of the second, which is minus 2, because alpha is equal to 2. So we have minus 2 times e to the minus 2t. And of course, I can replace A1 by minus 19.2 already. That makes things a little bit easier, 19.2. So that's A1. A2 is unknown. We have the alpha here, the negative alpha, because we have to bring it down when we take the derivative, and we have e to the minus alpha t, plus the second, e to the minus 2t, times the derivative of the first, and the derivative of the first is going to be, well, the derivative of A1 is 0, and the derivative of A2t is simply A2. Of course, the derivative of the steady state voltage 24 is equal to 0 as well. So now we can use this equation right here, where we can say that dV dt, and let me get out of the way so you can see it. So dV dt is 1 over c, and the initial condition of dV dt is the initial current over c. So what we can say here is that dV dt with a time equal to 0 is equal to I initial over c. And we're given I initial is equal to 4.8, and c is equal to 1/4. So that would be equal to 4.8 divided by 1/4, which is equal to 4 times that, which is equal to 19.2. So now, since that's equal to 19.2, we can set this equal to 19.2 when we take the initial condition. So dV dt, when time is equal to 0, is equal to 19.2, which is equal to this with t equal to 0. Now, when t equal to 0, this becomes 1, this becomes 1, and this goes to 0, so end up with minus 2 times a minus 19.8, which is 38.4, plus A2. And then, of course, when we subtract 38.4 from both sides, we can then say that A2 is equal to 19.2 minus 38.4, which is minus 19.2. So it looks like A2 has the same value as we got for A1. So now we're ready to plug that into our original equation. So the voltage as a function of time is equal to A1, which is a minus 19.2, plus A2, which is also a minus 19.2, times t, and the whole thing multiplied times e to the minus alpha, e to the minus 2t, and the steady state voltage is plus 24. Of course, we can pull out a minus 19.2, so this is minus 19.2 times 1 plus t, e to the minus 2t plus 24, if you want to write it in a more succinct form. All right, so now we have an equation for the voltage as a function of time. Now, how do we find the current as a function of time? So let's go back over here and notice that the current is simply C times dV dt. So we can use that equation again. So we'll use it over here. So I equals C. Now C is 1/4 times dV dt, which we have over here. Of course, we need to clean things up a little bit because we now know the value for A2. And let's see here what that looks like. So that gives us times minus 19.2 minus 19.2 t multiplied times minus 2 times e to the minus 2t, and then we have plus times an A2, that becomes minus 19.2 times e to the minus 2t. Now, I think we can probably combine some things here. Let me close the bracket. So here we have a minus 19.2 times minus 2, minus 19.2, all of it times e to the minus 2. So that's 3 times 19.2, that's looks like 57.6 if I'm not mistaken. 19.2 times 3 equals 57.6. Let's see. Oh, wait a minute. This times a minus 2. Minus 2 times this is a plus 38.4 minus 19.2. So I equals 4 times 38 minus 19. That's 19.2. And here we have a plus 38.4 t, all multiplied times e to the minus 2t. And then finally, we multiply this times 1/4, not 4, but 1/4. We divide everything by 4. 19.2 divided by 4 is 4.8. So yeah, I equals 4.8 plus 9.6 t, all multiplied times e to the minus 2t. And that gives us the equation for the current as a function of time. Notice there's no steady state current. It's got to be 0. Of course it's 0 because once we open the switch, once the capacitor fills up, there's no more current flowing, so ISS will be 0. And so that would be the final equation for the current as a function of time. And that is the current. And then here we have the voltage. Where's my voltage equation? Right here at the bottom. So here's my voltage equation. That does have a steady state voltage, and here's my current equation. And that is how it's done. And I only need one part because I managed to get it all on one board.